the fundamental frequency of a stretched string and the fundamental modes of vibration. To find the fundamental frequency, let us consider a string of length L which is held taut under a tension between two rigid boundaries. So let this represent rigid boundary, and we have a string of length L which is held taut with a tension T between these two rigid boundaries. Now if the string is excited, wave pulse travels through the string. A wave pulse traveling towards, say, the positive x direction, that is towards right here, gets reflected from the rigid boundary with a pi phase difference so that it gets inverted and travels in the opposite direction. The two identical waves traveling in opposite directions superimpose and form a standing wave, also known as a stationary wave. So during the fundamental mode of vibration, the standing wave is formed like this. That means the string will vibrate like this. These two positions forms the nodes, and this position at the center forms the antinode. Now this is the fundamental mode of vibration. It is known as a fundamental mode because it is the simplest mode. Now what is the simplest mode? The simplest mode in forming standing waves is when minimum number of nodes and antinodes are formed. We can see that these 2 points are fixed. It cannot vibrate. That means minimum number of nodes is 2, and by default minimum number of antinode will be 1. So minimum 2 nodes and 1 antinode, this makes the simplest mode of vibration, and this is known as the fundamental mode of vibration. The frequency corresponding to the fundamental mode of vibration is known as the fundamental frequency of the string. The frequency is given by the ratio of velocity to wavelength. Now what is the wavelength here? In the usual sense, the wavelength is defined as the distance between 2 consecutive particles which are in the same phase of vibration. Alternately, we can say that these are the positions where the 2 consecutive crusts are formed, or that between 2 consecutive troughs are formed when the particles are in continuous vibration in the medium. Now this distance represents half the wavelength. So we can say the length of the string in this situation is half the wavelength, L equal to lambda by 2, where lambda is the wavelength. So we can write the wavelength of the wave formed here as equal to 2L. So V is equal to, velocity is, the velocity of transverse wave in a stretched string is root of T by M, where M is the linear density and T is the tension, and 1 by lambda will be replaced with 1 by 2L. So this is the expression for frequency of the wave formed. Since this is the fundamental mode, this is the fundamental frequency. The fundamental frequency is also known as the first harmonic. The higher modes of vibrations are known as the overtones of the fundamental mode of vibration. So the next higher mode of vibration is known as the first overtone. Now, how will we find what is the next higher mode of vibration? Here there are 2 nodes and 1 antinode. The number of nodes and antinodes gets incremented by 1 in the next higher mode of vibration. That means in the next higher mode of vibration, we will be having 3 nodes and 2 antinodes, so that the string in the next higher mode, that is the first overtone, will be vibrating as at an instant, and then will be moving along, so that this is the first overtone. And we can see that the length of the string is the wavelength here. So the frequency corresponding to the first overtone, using the general formula V by lambda root of T by M velocity, 1 by lambda is 1 by L. This is the first overtone. We can see that the first overtone is 2 times the fundamental frequency. We will get the first overtone by multiplying the fundamental frequency, that is the first harmonic, with 2. 2 gets cancelled and we get this equation. So this is also known as the second harmonic. N times the fundamental frequency is the nth harmonic. So 2 times the fundamental frequency is second harmonic. So this is the first overtone and the second harmonic. And in the next higher mode, which is the second overtone, yes, as the general rule follows, the number of notes and antinodes will be incremented by 1. So for the same strength, for the same segment L, there will be 3 antinodes and 4 nodes. So we have 4 nodes and 3 antinodes in the next higher mode of vibration. So this distance makes up lambda, and the remaining distance is half the wavelength, lambda by 2. So lambda plus lambda by 2 will give 3 lambda by 2. So the length of the segment is 3 lambda by 2. That means lambda will be equal to 2L by 3. So it is again easy to write the second overtone, which is obtained from the same formula, velocity divided by wavelength. Wavelength is 2L by 3. So 1 by lambda is 3 by 2L. This is the third harmonic, since this is 3 times the fundamental frequency. So first overtone is the second harmonic, second overtone is the third harmonic, etc. So we can see that the nth harmonic will be n times the fundamental frequency, following the same pattern, where n is equal to 1, 2, 3, etc. are the number of harmonics.